Hi guys, today I would like to introduce a new concept. So to understand that concept, let us observe the diagram which is on the screen. So think about the case at here, how this charged comb, this is a charged comb. So we know that how to this comb gets charged. Suppose if we can do vigorously combing, so this plastic material gets charged. Now here this question, so these are the piece of papers. So these papers, how this charged comb attracting, and initially these are not charged, they are neutral. So how a neutral, that is also a piece of paper, it's not a conductor, it's an insulator. How insulator is affected by this charge? So to understand that, I would like to recall, so what are the charging methods we learned so far? So we learned about charging by friction. So this is the one of the method we learned, and one more method, that charging by induction. Yeah, this induction is a three-step process, so little difficult than the charging by friction. And this induction can done to metals, so it cannot be possible to insulators. So it's a three-step process, and it can be done to metals. And in each step we need to take it out the extra charges via path, here the conducting path or the ground, so which is the leftover charge, so that will be present on the charged objects. So this is the another method to do charging by induction. So today I would like to introduce another same type, but we cannot call it is charging by polarization. It's just a concept of polarization. So what is meaning of polarization? Suppose this is a neutral object. Suppose if you can take it as a non-conductor, a wall, a neutral body. So to this neutral body, if you bring a charged object, so this is the charged object, this is the charged balloon. Now if this charged balloon is close to neutral object, so what happens? The effect of this charge, and at here you can closely observe, suppose this neutral object is a conductor, so that conductor having the tendency of the electrons to move within the metal surface. But it's same, if I take this neutral object, it's not a conductor, it's an insulator. So in the insulator there is no free electrons. Electrons, they don't move on the surface. That is only possible for the conductors. But insulator, if you bring a charged object close to insulator, so the effect of the charged object on this insulator causes the orientation of the molecules. Now here you can observe one more time. So if this is a neutral object, so here you can see the positive charge and negative charges, they are electrically neutral. But when we bring this charged object close to the neutral, so something is happening in this neutral object. So what is the something? There is a no displacement of the electrons here. Electrons are not displacing, but the entire charge or the entire molecule, So what are the molecule is made up of that insulator? So that molecule are atom. So they are orienting. They are orienting such a way like that. Now here you can see, since it's a positive charge, now all the negative charges, now these all the negative charges are trying to attract this positive charge. Now here you observe that orientation, or if you can take a single word, or alignment. The alignment of these molecules, alignment of molecules, alignment of molecules due to because of this charged object. Now that process we termed as polarization. So it's a similar type charging, but once you take it out this positive charge, suppose if you take it out this positive charge, again the alignment will becomes to its same positions, it won't remains forever. So that's why this we cannot call as an exactly a charging method, but it's one type of charging, you can assume that. So how long this charged object present close to that neutral object? So in the neutral object, the molecules align, they will rotate and they will change their particular position. Now that process we known as polarization. Now as I asked the first diagram, so in the first diagram what is the cause? So here the cause is not due to friction, it's not due to induction, it's due to polarization. So these piece of papers, they are insulators, non-conducting, are attracting towards to the charged cone. It is due to because of the alignment of the molecules inside the non-conducting material or inside the insulator. That causes they are attracted towards to the charged object, and this process we termed as charged by polarization. So let us understand deep what it causes and what are these effects. So let us see how this polarization affects in metals. Yeah, this polarization, it affects both of the metals and insulators. For the both it is the possible. Let's understand polarization in metals. Suppose here I am having a stimulation. So in this stimulation, it's an aluminum can. So aluminum is a metal, it's an aluminum can. Now this is the initial state, it's having both electrons all over the metal surface. Now if I'm here, I'm having the two options. If I can just take rubber rod, now here it is my charged object, rubber rod. Now this is negatively charged object, rubber rod. Now this negatively charged object is attracted by the aluminum can. So even it is so far, now that can wants to touch the rubber rod because the displacement of electrons on the can. So can is having, it's a conductor, it's having free charges, and free charges can move on the metal surface. So if they can move on the metal surface, so they can go one side, but positive charge wants to attract the rubber rod. So here the process of separation of charges is not due to because of the friction, it's not due to because of induction, it's due to because of polarization. So polarization also affects in the metals. Suppose if I take it out this rubber rod, and again the electrons will be aligned into the same positions. So they will come towards to that. Now they will attract each other. Now similarly, if you can take a glass rod having as a positive charged object. Now since it is in a positively charged object, the electrons in the metal can now wants to attract the metal can. Since the metal can is having negative charges, now here the how the charges are the moving on the surface, it is due to because of the polarizations. So polarization affects the metal surface, the electrons will move within the metal surface. Yeah, we are familiar with this effect. So just you can observe how the water is leaning towards to the balloon, or it's curving. Suppose if you take this as a charged balloon, it is a negatively charged, and water, it's a non-polar molecules, which is having, sorry, it's a polar molecule which is having this kind of structure. Now if we bring this negatively charged balloon close to the water, now the bending of water is happens due to because the water molecule is contain positive charge. Now the positive charge of the molecules is the earlier case if you do not bring the negatively charged object close to the water. Suppose just to take as an let the water stream go. Now when you bring as an this charged balloon, so charged balloon is having negative charge, and a water molecule structure is, it is having negative charge and a positive charges, and the bending is happens. The bending is happens here, it means the water molecules are changing their position. So how they are changing? They are changing due to because of the external presence of the negatively charged. So this I can take as an external electric field or external field. That is a negatively charged external electric field. This is the original alignment. That is the original alignment. But when this presence of the charges, the polarization takes place in the water molecules. Now the water molecules, they turned, and this effect we called as polarization. Now that's the reason what could be the cause of the bending of the water stream. It is not due to because of the charging by friction, it's not due to because of the charging by induction, it's due to because of the polarization. And this effect is not permanent. Suppose if you take it out the balloon, so obviously again the water stream, it will be fall just like a straight line. Now we can bring the molecules, sorry, the charged object close to again the same polarization takes place. So again the water stream will bend. So here this effect is known as polarization. So this is the effect of the external electric field on the polar molecules or the non-polar molecules. Now finally I would like to define what is polarization. So whether polar or non-polar molecule, a dielectric develops a net dipole moment in the presence of an external field. So here first time I am using a word that is dipole moment. So whether a polar molecule or non-polar molecule, a dielectric develops a net dipole moment in the presence of external field. Now that dipole moment per unit volume is called as polarization. So let me discuss how this dipole moment is occurring in the presence of electric field. Again, one more time you can see the definition. Polarization, when it's a polar molecule or non-polar molecule, a dielectric develops a net dipole moment. I hope you remember what is the meaning of dipole moment. So for that, let me take you at here. So this is the non-polar molecules. So if it is a non-polar molecules, what is according to definition? According to definition, that the center of mass of positive charges coincide with the center of mass of negative charge. So here you can see. So this is the location where the center of mass of both the charges, positive and the negative charges, they are the coincides. So that's why they both are involved. Suppose if you want to locate where the center of mass, the center of mass is exactly at the middle. So that happens when there is no external electric field. Here the E suffix not equal to 0. It means there is no external electric field. So in that case, positive charge and negative charge, if it is positive charge, you can draw very small, and if it is a negative charge, you can draw as a cloud. So to locate where is the center of mass, so you can put at them exactly the midpoint. So that is the midpoint location of the center of mass for the non-polar molecules. So that is the molecule shape in the in the absence of the external electric field. Now here you can see the next diagram. Suppose if you applied certain electric field, now the electric field is not 0. It means it is not equal to 0. Now you just notice how this molecule changes its shape. Before it was perfect a sphere or perfect a circle, but when you applied an external electric field, suppose here in this case if I apply electric field at here, so if I draw electric field for positive charge for a moment, so this is the positive charge electric field I applied. Now this is the external electric field. Now this external electric field affects the molecular structure or atoms alignment. Now the positive charge attracts what? It attracts negative. Now the negative charge, now here you can see the atom's shape has changed. Before it was a perfect circle. Now here the location of the center of mass of the negative charge is changed. If the location of the center of mass of the negative charge change, automatically the molecular position has changed. It's something just like some dumbbell like structure. So that causes here a dipole moment. So what is a dipole moment? So dipole, we can define a dipole. Dipole we will define like that: a two oppositely charges separated by a distance. Now in the earlier case there is no distance because the center of masses are coincide. Now but in this case they are separated. Now in this particular case what happens? So they all are having dipole moment. So you remember dipole moment P is equal to the product of the charge times dipole length. So dipole moment is a vector. It has to supposed to show from the negative charge to positive charge. So here I can use a word. So that word is calling an induced dipole moment. Yeah, polarization causes induced dipole moment in the atoms or molecules. So that induced dipole moment affects the molecular structures. Now the external electric field, it causes the induced dipole moment within the atoms. So that's the reason. So how these, even though they are the non-conductors or insulators, they are affected due to the external electric field, because the external electric field causes induced dipole moment in the atoms of the polar molecules, non-polar molecules. In this case, suppose if I take the same for the polar molecules. So for the polar molecules, according to definition, the center of mass of the positive charge does not coincide with the center of mass of negative charge. Yeah, here we can see. So this is one of the structure of the non-polar molecule. Yeah, their center of masses are not coinciding. So in the absence of the electric field, so these molecules are randomly orientated. So that is due to because of the thermal agitations. So that automatically happens. So they are randomly oriented, and particularly you observe. So they are particularly, if you can observe that the positive charge and the negative charges of the two opposite molecules, so they are electrically neutral. Okay, now so that is the alignment of the molecules of the polar molecules or the polar dielectrics in the absence of the electric field. Okay, now if you take in this case, what is the total dipole moment? Dipole is a scalar. Now the dipole moment in this case, so the dipole moment we used to represent always from the negative charge to positive charge. So in this case in this direction, in this case in this direction, so in this case in this direction. So the dipole moment always from the negative to positive charge. So if you can take, they all are the randomly oriented. So the sum of the dipole moments, so the sum of the dipole moments sigma p in this case equal to 0. Yeah, because they are the randomly oriented. So the net dipole moment is a squarer, so we can add it up. So here they do not contribute any dipole moment in the absence of the external electric field for the polar molecules. But once you applied an external electric field, here in this case the external electric field is not equal to 0. Now the effect of the external electric field, so these molecules started to align. So they will align in that particular electric field direction. So they all oriented in one particular direction. So that is the net dipole moment direction. Okay, if that is the net dipole moment direction, so in this case the net electric field, because of this dipole alignment, that is also not equal to 0. Now this causes certain electric field effects due to because of the polar dielectric materials. So this is the how a non-polar molecules or the polar molecules will align in the presence of the electric field. So how they behave in the absence of the electric field and how they behave in the presence of the electric field. So let us visualize much more with the help of pH stimulation. So I'm having a pH stimulation. First let me take a non-polar molecules which is having a function of the just like N2, O2 or H2 like that. So if you can take that molecule structure just like a linear structure it comes. Suppose if each atom, these are made up of the two different, if you can take the molecules, and here if you can observe at here I am having the electron negativity. So if we can show their electron negativity at here in terms of the partial charges, or if we can increase or the decrease the electron negativity, so it means in that case the particularly that charge will be more negative. So suppose this atom, not the charge, atom, suppose this atom is having very less electronegativity and this atom, atom B, is having some electronegativity. So let me take this as a more. So this is the alignment of the this particular molecule in the absence of electric field. Now if I take, if I switch on the electric field at here, now if you can apply the electric field at there, now since it is a positive charge plate, it's a positive charged plate and it's a negative charged plate, and the B is having the more electron negativity, it means it is having as a more electrons, so that's why it is attracted towards to the positive plate. Suppose if I make A as more electron negativity than the B, now here you can see, now the molecules is aligned, it's rotated, it's changed its direction. Now if you can do that one more time, now if I take A is less and B is more, now atom B is more negatively charged. Now that more negatively charged wants to attract positive plate. Now again the atom is aligned or change in position or the rotation. Now the atom is aligned in the presence of the electric field. Now here you can see the dipole moment. Now this is the external electric field direction from the positive charge to as a negative charge. Now here you are representing as a bond dipole, not atom dipole, it's a bond dipole from the less positive to as a less negative. Now my intention to show that how this alignment takes place in the presence of the electric field and in the absence of this, when it do not takes place in the absence of the electric field. Suppose if atom A is having little less than that ones, now here you can see that alignment, how nicely the molecule structure, the structure is rotating in the presence of the electric field. Now that rotation due to presence of the electric field we are calling as a polarization. So this polarization happens in the two atom molecules. Suppose I am having another 3 atom molecules. Suppose if I take 3 atoms in this case, so it appears just like structure of water. Now any structure you can take. In this case I am having help of molecular dipole. Yeah, this is the total molecular dipole. And here first you can observe, see the atom C electron negativity is very less, and atom A is electron negativity is also less, and atom B which is having electron negativity. So that is the resultant dipole moment direction. Now, if I switch electric field at here, now what we would expect that? Now we would expect that the atom B will takes clockwise direction. So when I can switch the electric field at there, now before the switch off, so that is the rotation, it's already aligned. Now if I can take little more further, or if I can switch the alignment of these molecules, so in the presence of the electric field, so let me take off that first. So let me reset. If I reset, then it's easy to make you to understand. Come on, baby. Now this is the location. I would like to make it slow motion. Now if I turned the electric field on nicely, the atom is aligning with in the presence of the electric field. Now here the main point, if this is the electric field direction and this is the resultant dipole moment direction, now that is a single molecule. Just imagine I am having now three-dimensional. Now I would like to define polarization. Polarization means nothing but the dipole moment per unit volume. So that's the definition of polarization. So dipole moment per unit volume. So in that case, if I take this as a 3-dimension, so or a simplest case, if I take, I'll take just a cube. So a cube of just like something. Now if you take this entire molecules within the cube, since we have to define per volume. Now if you take, these are the charges of the positive, so now these charges within the cube, they will align, it's a positive charge. Now they will go align positive charge because they have to attract towards to the negative plate, and this side, if it's a positive charge, they will attract to the negative charge because the B atom is having electron negativity. Now that negative atoms towards to the negative charge. Now what is the in between? In between, the total dipole moment, or if I can call in another words, the total electric field, that contributes to 0. So let me take one more diagram to make you better understanding. Yeah, let's observe this diagram at here. Suppose I kept a polar molecule or non-polar molecule within the electric field. So this is my external electric field direction. Now here in this case, you need to observe in the 3 dimensions. On the screen we can see only the 1 dimensions, but you can observe that as in the 3 dimensions, because I need to define the polar molecule as polarization as the dipole moment per unit volume. We need to define dipole moment per unit volume. So this box you can just imagine as a 3 dimension. Now we learned that because of the presence of the external electric field, so this is the external electric field direction. So the molecules, maybe before they are like that, now they are changed the shape, so that is the shape they got. And here you can see the dipole moment direction. Now there is a dipole moment alignment is there, but if that is the dipole moment direction, you closely observe. If I take a location of this location I would like to identify what is the total electric field. So the total electric field within this location where the dotted square has drawn. So in this case, the total electric field inside the dielectric material, the total electric field inside the dielectric material, that contributes to 0. Why? Because the electric field is 0. Because according to Gauss theorem, closed integral E dot ds equal to q by epsilon naught. Here the total charge is the net charge. The net charge in this case equal to 0. If you can closely observe, the total charge of the positive and the negative charges within this dotted rectangle. Within that dotted rectangle, the net charge net, that equal to 0. So if that charge equal to 0, so we won't expect any electric field within the inside of that dotted circle. Yeah, that point is agreed. But so other than that, if you can notice, since it's a 3 dimensions, so if it is 3 dimensions, one face is having the negative charges because of the alignment of the polar molecules. So these are the negative charges in the one side, just like you can imagine, just like a book or a brick. Since it's the 3 dimensions, so this side will be one type of charge. So in this diagram is showing as a negative charge, and this side it will be accumulated as a positive charge. Now that is not within the dotted circle. Now that is the diagram here I highlighted. So this is the positive charge and this is the negative charge. Now these two separate charges are at the surface or at the edges of the material. Now they contribute certain electric field. So in this figure you are seeing 3 electric field terms. So E naught is the applied external electric field, and E suffix P, which is the electric field due to these charges from the positive and due to the negative charges because of that, and they contribute the electric field from the positive to negative charge, so in this direction. Now that we represent the E suffix P. Now here you can see, if E naught is the applied external electric field and the E suffix P is the electric field due to polarization within the dielectric slab. Now this electric field is not exactly equal at here. If you remember, if you take conductors, so if you take conductors, a conducting sphere is presented external electric field. So this is the external electric field. Now within the conductors, electric field is also develops exactly the same in the opposite direction. Therefore the total electric field within the conductor equal to 0. So that's why on the surface of the conductor electric field is 0. So that is the properties for the conductors. But when it comes to insulators, or insulators are nothing but the dielectric, the total electric field is not equal to 0. So the electric field total is not equal to 0. There is certain residue or the leftover electric field. So here the leftover electric field is E. So the leftover electric field E equal to E naught minus EP. So which is the residual or the leftover electric field within the dielectric material. So that electric field is the advantage for us. So we will make use of that. So here I can write the external electric field E equal to applied electric field E naught minus E suffix P. Here it is the electric field due to polarization of the charges in the presence of the external electric field. So this peculiarity only happens to these insulators. But for the conductors, so even though they get, but the result will becomes to 0. So that's why we'll use this dielectrics to increase the strength of the electric field. Now that is the main advantage of the uses of the dielectrics in an external electric field. So finally I can say at here, if we keep a dielectric in the presence of external electric field, dielectric in the presence of external electric field, there will be residual. So there will be residual electric field. So the electric field due to polarization. Now that electric field will be opposite to the applied electric field. Now if they both are opposite, now if you can subtract, there will be electric field which that will be present in the dielectric material. So here the electric field in dielectric, which equal to electric field due to the external minus electric field due to the polarizations. And this electric field is help us certain things which will happen when we keep this dielectrics in the presence of the electric field. So that's the concept of the dielectrics and the polarization. So in the next we will understand how this relate the dielectric constant and dielectric of different materials.